Ask My Instructor 15.7.16. Given a vector field F and a curve with counterclockwise direction, given these two things, we want to evaluate the line integral by evaluating the surface integral in Stokes' theorem with an appropriate choice of S. Those are the instructions. To understand the instructions, let's do a short review. Remember that in Green's theorem, net circulation of a vector field F on a curve C, where C is the boundary of a region R, can be found by adding up two-dimensional curl at each point in the region R. So the cumulative rotation of the flow within the region equals the circulation along the boundary. The same idea is going on with Stokes' theorem. The net circulation of a vector field on a curve where the curve is the boundary of a surface S can be found by adding up the components of the curl in the direction of the normal vector at each point on the curve S. And so here's a diagram of what's going on. Net circulation of the vector field F on the curve, which is the boundary of the surface S, can be found by adding up the component of the curl in the direction of the normal vector at each point in S. In the diagram, the brown vectors are the normals for the surface, and the red vectors are the some of the vector field vectors, and the green is the curl, and so you would want to find the dot product of the green with the brown and integrate over the surface. And here is Stokes' theorem if you want to turn off the video and look at Stokes' theorem in its as it is formally stated. So Stokes' theorem involves an oriented curve C and an oriented surface S on which there are two normal vectors at each point. So one's going to be pointing, if you will allow me, one's going to be pointing up and one's going to be pointing down. So at each point, the normal vector could be either up or down, oriented with the surface. So the orientation of the normal vector and the orientation of the curve needs to be consistent. And what we use is a right-hand rule that relates the orientation of the curve and the orientation of the surface and determines the choice of normal vectors. If the fingers of your right hand curl in the positive direction around C, then your right thumb points in the general direction of the vectors normal to the curve, normal to the surface S. Our curve consists of the three line segments that bound this plane in the first octant oriented as shown. The line integral would involve the parameterization of three line segments. Instead, we could find the surface integral form of Stokes' theorem, where S is that portion of the plane that lies in the first octant. Since the surface is defined by z equals 20 minus 4x minus 5y, we can use this parameterization. Have x just be x, have y just be y, but then have z equal 20 minus 4x minus 5y. So using that parameterization, n is going to be plus or minus z partial x, negative z partial x, negative z partial y, 1. And we need to choose n so that it's consistent with the counterclockwise direction of the curve. So z partial x is negative 4, z partial y is negative 5, and so our normal vector is plus or minus 4, 5, 1. We need to choose the direction so that n is consistent with the counterclockwise direction of the curve. So looking at the graph, you can see that the positive vector 4, 5, 1 follows the right-hand rule. So what is the region R? And why do we want to find this region R? We are at this point in our Stokes theorem. We have found our normal vector n, and we're going to want to integrate over R, where R generates the surface S. We need to find where the plane Z crosses the xy plane. So let's look at that. If z equals 20 minus 4x minus 5y, if both z and y equals 0, then x would be 5. So it crosses the x-axis at 5, 0, 0. And again, looking at z equals 20 minus 4x minus 5y, if z equals 0 and x equals 0, then y would have to be 4. So those are our 2 points. And so this is our region R, and we need to find the equation of the line. The line is y equals negative 4/5 x plus 4. And so the region R is y runs between 0 and the line, and x runs between 0 and 5. So we have our region R that generates our surface S, which is the plane z equals 20 minus 4x minus 5y, located in the first quadrant. All right, so this is where we are now. We have found our region R, and the only thing left to do is to find this cross product. So the cross product is the curl, and so we are in the job now of finding the curl. The first component of the curl is 0. The second component of the curl is also 0. And the third component of the curl is 0. So our dot product in that case is going to be 0, and we're doing a double integral where our integrand is 0, and so of course the integral is equal to 0. Alright, so we are done with the problem. Just one final comment I want to make. I organized this video the way I did because it's not always going to be the case that the curl is equal to 0. In this case, the curl of delta cross f, the curl is equal to 0. And I actually knew that. And it may be worth your while to find the curl first and hope that it's your very lucky day. If the curl is equal to 0, you don't have to find the normal vector. You don't have to find the region. And I knew that the curl was 0, and I could have just stopped and said the curl is equal to 0, and so the line integral is equal to 0. The reason why I didn't do that is I wanted you to see the process of finding the normal vector n, and to see the process of finding the region R, in case you come across a problem either in the homework or on a quiz or on a test where the curl is non-zero. Alright, so I'm done here, and take care and have a great day.